Glass, a material often taken for granted, surrounds us in countless ways. From windows that illuminate our homes to the screens of our smartphones, glass plays a vital role in our modern world. Its transparency, durability, and versatility make it indispensable across various industries. Glass is an amorphous solid, meaning its atoms lack a regular, repeating structure. This gives glass its distinctive properties. Its transparency allows light to pass through, ideal for windows, lenses, and optical fibers. Its hardness and resistance to scratching make it suitable for everyday use. The history of glassmaking dates back thousands of years, with origins in Mesopotamia and Egypt. Today, scientists and engineers continue to push the boundaries of glass technology. From the mundane to the extraordinary, glass shapes our world in remarkable ways. When we think of strong materials, steel and diamond often come to mind. Glass, with its reputation for fragility, might seem like an unlikely candidate for strength. However, glass possesses surprising strength, especially when considering its structure and composition. To understand and quantify this strength, scientists use a test called the Vickers micro-hardness test. The Vickers micro-hardness test measures a material's resistance to indentation. In this test, a diamond indenter shaped like a pyramid is pressed into the surface of the glass with a specific force. The size of the indentation left behind is then measured under a microscope. A smaller indentation indicates greater hardness and therefore greater strength. The Vickers micro-hardness test provides valuable information about the mechanical properties of glass. It helps engineers and scientists select the right type of glass for specific applications, ensuring its durability and performance. For example, glass used in smartphone screens needs to be incredibly hard to resist scratches, while glass used in building facades must withstand wind loads and impacts. The Vickers micro-hardness test is just one of the many tools used to characterize the remarkable properties of glass. By understanding its strength and other mechanical properties, we can unlock the full potential of this versatile material. While glass exhibits impressive strength under certain conditions, it is also inherently brittle. This means it tends to shatter upon impact. The brittleness stems from its amorphous structure. Scientists have developed methods to enhance glass toughness. Techniques include altering composition or strengthening during manufacturing. One method is thermal tempering. Heating and rapid cooling create compressive stresses. These stresses increase resistance to impact. Another method is chemical strengthening. Glass is immersed in a molten salt bath. Larger ions replace smaller ones, creating compressive stresses, used in smartphone screens and aircraft windows. Beyond strengthening the glass itself, another approach to enhancing its safety and performance is lamination. Laminated glass, invented in the early 20th century, consists of two or more layers of glass bonded together with a layer of polyvinyl butyryl (PVB) interlayer. This PVB interlayer acts like a tough, transparent glue, holding the glass layers together even upon impact. When laminated glass experiences an impact, the PVB interlayer absorbs and dissipates the energy, preventing the glass from shattering into dangerous shards. Instead, the glass may crack, but the fragments remain adhered to the PVB interlayer, maintaining a barrier and reducing the risk of injury. Laminated glass revolutionized safety in various applications. In automobiles, it became the standard for windshields, protecting occupants from ejections and reducing injuries from flying glass. In architecture, laminated glass provides security, sound insulation, and protection against forced entry. Its ability to hold together even when cracked makes it ideal for skylights, balustrades, and other overhead glazing applications. Section 5. The electrical secrets of glass. Contrary to what some might believe, glass is not always an insulator. While most commonly encountered glass compositions act as excellent electrical insulators, certain types of glass exhibit surprising conductivity. This electrical behavior of glass depends on its composition and, importantly, its temperature. In general, glass at room temperature acts as an insulator because its electrons are tightly bound to its atoms, preventing the flow of electrical current. This property makes glass invaluable for applications like electrical insulators in power lines, circuit boards, and various electronic devices. However, as the temperature of glass increases, its electrical conductivity also increases. This phenomenon occurs because the heat provides energy to the electrons in the glass, allowing them to break free from their atomic bonds and move more freely, thus conducting electricity. This temperature-dependent conductivity of glass has led to its use in specialized applications like glass electrodes for measuring pH and other electrochemical properties. Moreover, certain types of glass known as chalcogenide glasses exhibit even more pronounced conductivity, making them suitable for use in memory devices and other electronic components. Section 6. A spectrum of colors transforming glass. The natural transparency of glass is undoubtedly one of its most appealing qualities. However, glass can also be transformed into a canvas for a vibrant spectrum of colors, adding both aesthetic appeal and functional properties. From the stained glass windows of medieval cathedrals to the tinted windows of modern skyscrapers, colored glass has captivated human imagination for centuries. The art and science of coloring glass involve introducing metallic oxides or other colorants into the molten glass during the manufacturing process. These colorants absorb specific wavelengths of light, allowing others to pass through, resulting in the perception of color. For example, adding cobalt oxide to the glass melt produces a deep blue hue, while chromium oxide yields emerald green. Gold chloride creates a ruby red color, and a combination of sulfur and iron oxide produces amber tones. The exact color and intensity depend on the type and concentration of colorants used, as well as the melting temperature and other factors. Colored glass serves both decorative and functional purposes. In architecture, colored glass adds visual interest, controls solar heat gain, and reduces glare. In signal lights, colored glass ensures clear and unambiguous communication. In art and design, colored glass offers endless possibilities for creative expression. Section 7. Chemical resistance, glass's enduring nature. One of the remarkable properties of glass is its exceptional chemical resistance. Unlike many other materials that corrode, degrade, or react with various substances, glass remains largely inert to most chemicals, making it an ideal material for a wide range of applications. Glass's chemical resistance stems from its strong chemical bonds and its non-porous structure. The silicon-oxygen bonds that form the backbone of the glass network are highly stable and resistant to attack by most acids, alkalis, and solvents. Additionally, the lack of pores or voids in the glass structure prevents chemicals from penetrating and causing damage. This exceptional chemical resistance makes glass an invaluable material in laboratories, where it is used to store and handle corrosive chemicals, conduct experiments, and manufacture pharmaceuticals. In the food and beverage industry, glass containers preserve the quality and flavor of products, preventing contamination and extending shelf life. However, it's important to note that not all glass compositions exhibit the same level of chemical resistance. Certain types of glass, such as borosilicate glass, are specifically engineered to withstand exposure to harsh chemicals and extreme temperatures. Section 8. Glass in action, from buildings to medicine. The versatility of glass extends far beyond its familiar uses in windows and containers. From towering skyscrapers to delicate medical devices, glass plays a critical role in countless industries, shaping our world in profound ways. In construction, glass has become an indispensable material, transforming the aesthetics and functionality of buildings. Large glass facades flood interiors with natural light, reducing energy consumption and creating a sense of openness. Insulated glass units enhance energy efficiency, while safety glass provides security and protection. In healthcare, glass is essential for a wide range of applications. Medical vials and ampoules store and deliver life-saving medications, while syringes and other medical instruments rely on glass's transparency and biocompatibility. Optical fibers enable minimally invasive surgical procedures and advanced imaging techniques. The automotive industry also relies heavily on glass. Windshields provide visibility and protection, while mirrors enhance safety. Headlights and taillights use glass lenses to direct and focus light, ensuring visibility on the road. Section 9. Conclusion: a transparent future. From the ancient art of glassblowing to the cutting-edge science of fiber optics, glass has captivated human ingenuity for millennia. Its transparency, strength, durability, and versatility have made it an indispensable material in countless applications, shaping our world in profound ways. As we continue to explore the fascinating properties of glass, we unlock new possibilities for its use in various fields. From energy-efficient buildings to life-saving medical devices, glass continues to push the boundaries of innovation, offering a transparent window into a brighter future. As we gaze through a pane of glass, let us marvel at the science and artistry behind this remarkable material. Its transparency connects us to the world around us, its strength protects us, and its versatility enables countless technological advancements. Glass, in its many forms, will continue to shape our world for generations to come.